Okay. Cool, it's going. All right, I'm going to start now. People can walk in as they come in. Recitation is running a little over this week, so. Let's get started. One up. And back. Create a new page. All right, cool. So welcome to Recitation this week. We're going to be covering 2.5, a little bit 2.4, which is like the rank stuff, but you're going to need to know that anyways for doing systems of equations. And then we'll talk about systems of equations extensively. And then in the last 5 minutes, I'll talk about how to find matrix inverses, and we'll probably run over a little bit. So again, I am recording this. I hope I'm recording this again. So it'll be online after Recitation today. So if you want to rewatch it, you can. But I've been pretty consistent throughout. So yeah, I looked at where we were last semester at Recitation 3, and we were at chapter 4.6, and we're on chapter 2.6. So we're going nice and slow this year, which is, I guess, that's good. But yeah, so if you think things are moving a little slowly in class, don't worry. That's definitely the case right now. So, all right, let's get started. We're going to jump into actual problems today. We'll actually be able to use my test bank of a lot of test questions I have. But before that, we're going to talk about some definitions, because why not? And so let's talk about rank and pivot. Okay, so what are rank and pivot? I'm just going to make sure I'm recording this again. I really don't want to just accidentally not record. Okay. Okay, so what are rank and pivot? So the definition of rank is the following. It's going to be the number of non-zero rows in the row echelon form of a matrix A. So that's what rank is. And so, for example, then let's just find the ranks of some matrices. So if I have the identity matrix, right, and let's say it's n by n, what would the rank of this identity matrix be? Yeah, it'd be n, right, because I'd have n rows of ones, okay? Cool. And then, let's see, let's take a look at 1, 2, 4, 0, 0, 3, negative 7, 1, 0, 0, 0, 0. Okay, what's the rank of this matrix? 2. Okay. Notice how it's not technically in row echelon form, but all we had to do was divide that second row by 3 anyways, so we would have gotten there. So okay, that's how we would have known that. And then the last one, this one's gonna be a little more tricky. 2, 1, 1, 1, 4, 0, 2, 0. All right, what's the rank of this matrix? 1, 3, 2, 4, 2. All right, so it is 2, but why is it 2? Well, what's the definition of rank? It's the number of non-zero rows in the row echelon form of a matrix. That's not in row echelon form, so we need to reduce this somehow. And so if I do row 1 minus row 2, we end up with 1, 0, 1, 1, 4, 0, 2, 0. And then we realize, hey, we can just kill the last 2 rows now, right, with the first row. And so this becomes 1, 0, 1, 1, a bunch of zeros. And then finally, to do proper row echelon form, I want to zero out that guy. And so 1, 0, row 2 minus row 1 gets me 0, 1. Okay, and then this rank we find is 2. Okay, so what could that matrix, what couldn't have been that rank? What are numbers that just make no sense in terms of the rank of that matrix?
1.
1 is okay. 5 doesn't make sense. It could be. Oh yeah, it can't be 0 because it's not a 0 matrix. That's right. Okay. Okay, sure. But right, so I was looking more towards like 3 or 4. Right. It's really tempting to say 3 or 4, but the rank of a matrix can't be 3 or 4, and that's because there's this important property you need to know. But for A, which is an n by n matrix, right? The rank of A has to be less than or equal to the minimum number of columns or rows. All right. So in this case, we had a 4 by 2 matrix, right? So we take the smaller number of the 4 by 2 matrix, which is 2, right? And we say, hey, the rank can't be bigger than 2, or it can be 2, but can't be bigger than 2. So keep that in mind. It could show up as a true-false problem. It's one of the things they tend to test, knowing that rank has that property. Okay, so 3 or 4 would not have made sense at all in the context of that problem. Okay, let's see. Let's talk about pivots then. Okay, so I'm not sure how the book defines pivots. I probably should actually figure that out. But in any case, I define pivots as where a leading one should be. Okay, so again, let's look at some examples, and it'll be a lot clearer. So let's just take this 3 by 3 identity matrix. All right, where are my pivots? Yeah, it's just they're on the diagonal, right? It's going to be that one, and that one. Okay, so it's where the leading ones should be. In this case, I actually have leading ones, so leading ones are where leading ones should be. Okay. The next example, let's take a look at this matrix up here that we just had. All right, 0, 0, 0, 0 on the bottom. Okay, where are my pivots here? Just shout the numbers out. 1, 3. All right, so, okay, and so I'm just going to call these guys the pivot columns, right? They're the columns that contain the pivots. And then I have 2 columns here that don't contain a pivot, and I'm just going to call these the free columns. All right, yeah.
So does the pivot refer to the number that's where the leading one is?
Yeah, so the pivot refers to what that number is there.
It's like 3, not 2, 2. Like not the coordinate like 2, 2.
It really doesn't matter. We never talk about that. You just need to know where the pivot is. That's all that matters. What's actually even more important is this discussion of pivot columns right here. That's going to be more important than what the pivot actually is. So, yeah, good question. So, all right. So I got 2 pivot columns, got 2 free columns. Now let's take a look at just another non-trivial example. Then 0, 5, 3, 1, -7, 0, 0, 0, 2, 0, 4. 0, 0, 0, 0, 5. All right, this should be a 4. Okay, so what are my pivots? Yell the numbers out. Okay, -5, 2, and 5, right? So those are where my pivots are. And then these are going to be the pivot columns because they have the pivots. All right. And so we write P underneath that matrix, and then the 2 columns that don't have pivots, they're going to be the free columns. All right. Any questions? Okay, cool. And so why do we talk about pivots? Well, this matrix right up here, we kind of just took the rank without ever actually reducing that to row echelon form, right? It's not in proper row echelon form. You needed a leading 1, so we had to divide it by 3. But why did we know the rank? Well, we knew the rank because we knew that it had 2 pivots, right? So if you look, there's going to be 2 pivots in that matrix. And so in general, then the number of pivots is going to equal the rank. of that matrix, and that's an easier way, just slightly less steps than reducing that matrix to like proper row echelon form. And I often say something along the lines of like expose the pivots, which just means like reduce it to a form where you can see where the pivots are. So that's what like exposing the pivots means. Okay, so keep that in mind. That's enough discussion of that. We'll actually move on then to chapter 2.5, which is Gaussian elimination. Really, this chapter is about solving systems of equations. Okay, and before we start, let's create this table. So we're going to deal with A being a 3x3 matrix for now. So again, what is A? We're solving that system. AX is equal to B. So A is going to be, this A is going to be a 3x3 matrix. Okay, and then M by L. This first column is going to be the number of solutions. The second column is going to be the rank of A. And this third column is going to be the rank of the augmented matrix. Right? So do we remember what the augmented matrix was? I talked about that in this recitation, I think, last week. But anyhow, we'll get to what that is. Okay, so there's that table, and now we'll take a look at some book problems first to motivate examples. Is this 2.5.6? I think so. Anyways, what do I have? I have the following system of equations. All right, 3x1 plus 5x2 minus x3. Okay, hold on. Okay, whatever, it doesn't matter. Okay, minus x3 is equal to 14. X1 plus 2x2 plus x3 is equal to 3. 2x1 plus 5x2 plus 6x3 is equal to 2. Okay, and so how do we set this up? Well, we want to write these in terms of a matrix. So I'm going to have this going on, where so I just put the coefficients of this of the rows into this matrix on the left-hand side. So this is 3, 5, negative 1. This is 1, 2, 1. And this is 2, 5, 6. All right, and then I put these guys into the right-hand side. And so I'll have 14, 3, 2. Okay. And so what is all of this? Well, this is what I call the matrix A, right? This part. That's going to be the matrix of coefficients. I always call that A. Here is B. All right, that's the vector on the other side of the equal sign. And this entire thing is going to be my augmented matrix A. All right, so how do I solve this system of equations? Well, I want to reduce it to, essentially, I want to expose the pivots, okay? And that often means reducing it to row echelon form. So let's do that. And what's going to be my first step? Well, we usually always want a 1 in this upper left-hand entry first. And so how can I do that? Yeah, just flip those first and the second row. So 1, 2, 1, 3, 3, 5, negative 1, 14, 2, 5, 6, 2. Right? Okay, and then the next step would be, I really would like to get zeros here. Okay, and that's usually what the next step is. So I want to get zeros there. And how would I get zeros? What kind of row operations would I have to perform? Yeah, so I want to subtract the multiple a row from the other rows, right? So for this second row, it makes sense if I do row 2 minus what? Yeah, 3 times row 1. All right, and then for the third row, it makes sense to do row 3 minus, 2 times row 1. So, okay, so first row stays the same. These two entries are 0 by construction, right? Because that's the entire idea, is we're zeroing those guys out. And then, okay, so now I got 5 minus 3 times 2, right? So I'm going to do these entries first. So 5 minus 6 is negative 1. Negative 1 minus 3 is negative 4. And then 14 minus 3 times 3, 14 minus 9, that's 5. Okay? And then row 3 minus 2 times row 1. So I got 5 minus 4, that's 1. 6 minus 2, that's 4. And then 2 minus 6, that's going to be a negative 4. Okay, so again, I said that we want to reduce it to like almost row echelon form, and this is an example where we don't quite have to reduce it to row echelon form because we can easily kill, because the next idea is we want to kill that entry, right? And it's pretty simple just to add then row 3 and row 2 together. So we didn't have to do anything with this guy, really. So now we just do row 3 plus row 2, and I'll get 1, 2, 1, 3, 0, negative 1, negative 4, 5, and this is 0, 0, 0, 1. Okay, so what do I have? What is that matrix telling me? Okay, so sure, right? Yeah, if we look at the number of pivots, right? So here's a pivot, here's a pivot, all right, and there's a pivot here as well, but we don't really care about that pivot because it's not right? Remember what do the columns correspond to? The variables, right? So this was x1, x2, x3, right? So this was the B column. Right, and it's okay, well, I have a pivot in the B column, sure. But now that I've written it out like this, what do you notice about the last row? Yeah, it's inconsistent in the sense that this is 0x, so in row 3, I have 0x1 plus 0x2 plus 0x3 is equal to 1. Alright, so 0 is equal to 1. Can't have that. Okay, so in this sense then, there's actually going to be no solution to this system. Okay, why is that? Why is there no solution to this system of equations? So maybe that table that we created earlier, maybe that'll help us in the sense. So in my table, it was number of solutions, rank A, and rank of the augmented matrix. Okay, so the number of solutions is 0. What's the rank of A? It's 2, right? Because remember, A is this guy. So A started out being this thing, but to find the rank, we had to reduce it to expose the pivots anyways, right? So rank A is 2, but what's the rank of the augmented matrix? It's 3, right? Because I got a pivot in the bottom right. Okay, so go back up here. Then, if you have no solution, the rank of A is 2, and the rank of the augmented matrix A was 3. Okay, and so something doesn't quite match up there, which is why we have 0 solutions. And okay, once we get more examples, we'll return to this. Any questions? All right. Okay, so now let's take a look at another example. It's 2.5.1. And are we okay if I don't write out the initial system and we just start with the matrix? Okay, we'll save some time. So So let's consider it in this system. 4, negative 3, 6, 2. 1, negative 3, 6, 5. Negative 2, 3, negative 8, negative 6. Let's talk about, okay, so again, I have x1, x2, x3. Those are going to be my variables, right? My unknown, my variables. And then this is my b column. And we didn't do this for the last problem, and probably should have, but essentially the past two recitations, right? We've been talking about like what the geometric interpretation of the system of equations would be. So what do I really have here, and what am I trying to find? So like, what space am I in, and what kind of shapes do I have in my space? Yeah.
I think it's 3D with 3 planes.
Yeah, so I have 3 planes in R3, right? And again, I'm just calling them x1, x2, x3, but if I called them x, y, z, then it would be immediately obvious to you guys that those are planes, right? Because that was pretty much all of 114. The 3 planes in R3. Up here, we also have 3 planes in R3. And I had no solution, which means what? Yeah, there's no common intersection, right? All right. Here's another question. Then, just real quickly, if there's no common intersection, is it because like 2 of the planes are parallel to each other? No, right? Because then the coefficients would be like a multiple. Like one equation would just be the other equation, but the coefficients would be like a multiple of each other, right? So yeah, that's not the case. Yeah, they're just like 3 planes that just don't intersect at a common point. That's nothing special about that. Okay. So in this case, then we also have 3 planes in R3. And all right, what do we want to do? What's the first step? Yeah, so we want a 1. Yep. So we're gonna switch. 1, negative 3, 6, 5. 4, negative 3, 6, 2. Negative 2, 3, negative 8, negative 6. All right. Step 2. Well, it's the 0 of those guys. All right. And so this will be row 2 minus what? 401. And what's the second operation I should perform? Yeah, row 3 plus 2, row 1. So row 1 stays the same. Okay, what does row 2 become? Well, that's 0. This is negative 3 minus a negative 12. So that's plus 12. This is 9. 6 minus 24, negative 18. 2 minus 20, negative 18. Okay, and then this becomes 0. 3 plus negative 6, negative 3. Negative 8 plus 12. 4, negative 6 plus 10. That's positive 4. All right. Okay, and so from here, right, what's the next step? Well, we probably want to put a 1 in the next pivot. All right, it'll help us out a little bit. So we want to put a 1 here. And how do we do that? Yeah, divide everything by 9. 0, 1, negative 2, negative 2. 0, negative 3, 4, 4. Okay, and then now we want to zero out this guy, which is row 3 plus 3 times row 1. Row 2, thank you. And so 1, negative 3, 6, that's a negative 3. 5, 0, 1, negative 2, negative 2, 0, 0, 4 plus negative 6, negative 2, negative 2. All right, that's good enough. We don't need to reduce that last row because the equation comes to us immediately. So from row 3, I get the equation, right? Negative 2x3 is equal to negative 2. All right, so I can just solve that. X3 is equal to 1. From row 2, I'll get the equation x2 minus 2x3 is equal to negative 2. And we already know what x3 is, so this becomes x2 minus 2 is equal to negative 2. And so x2 is equal to 0. And then from row 1, x1 minus 3x2 plus 6x3 is equal to 5. So this is x1 minus 0, since x2 is 0, plus 6 is equal to 5. I'll get x1 is equal to negative 1. And so my solution then is going to be negative 1, 0, 1. And what is that? Geometrically. Yeah, it's a point. Okay, so I got 3 planes in R3. Their common intersection is going to be a point. Okay, and so if I intersect at a point, then how many solutions are there? There's one solution. Okay, so again, thinking back to that table now, I have one solution. So remember, this is A, and then this entire thing is A augmented. So what's the rank of A? 3, right? So I end up having 3 pivot columns here, right? So rank of A is 3, and what's the rank of A augmented? Yeah, it's also 3. Since this guy isn't a pivot column anymore, right? So, okay, so if we go back to the table, then I had one solution, the rank was 3, and the rank of augmented matrix was also 3. Okay? And now, let's do one more example. 2.5.5, or is this number 15? I might have typoed. I don't know what problem this is. It's one of these two. So I have the following. I think there's a spot up there. 3, negative 1, 0. Let me rewrite this better. 3, negative 1, 0, and then 1. 2, 1, 5, 4, 7, negative 5, negative 8, negative 3. Again, got x1, x2, x3, and what kind of shape do we have? Like what shapes in what space? Yeah, 3 planes in R3. And I guess I didn't really talk about what this really means. How do we know we have 3 planes? Does that correspond to number of rows or number of columns? So I heard both. So I have planes, right? What do my columns represent? The variables, right? I've written them up there, x1, x2, x3. So the columns represent my variables, and each row represents then a plane, okay? So this 3 comes from, let's use a brighter color. This 3 is really the number of rows. I'll call this m, actually, since we always do like m by n. So 3 is the rows. And then how do we know it's in R3? Well, that's because that's the number of variables we have, right? And so that's n. Okay. Anyhow, All right, okay, so not as trivial. We can't just switch immediately, so what should our first step be? Yeah. Not quite 2 row 2.
Row 1 minus
Yeah. So row 1 minus row 2. Although I guess 2 row 2 also works, because you just get -1. But yeah. We'd rather deal with positive numbers. Oh, whoops, don't want to rewrite that. So we can write the other rows. Alright, and then row 1 minus row 2, that's a 1. -1 minus 1, -2. 0 minus 5 is a -5. 1 minus 4 is a -3. Alright, next up, zeroing out these guys. We'll do row 2 minus 2 row 1, row 3 minus 7 row 1. 1, -2, -5, -3, 0, 1 minus a -2, or 1 minus a -4, it's 5. 5 minus a -10, it's 15. And 4 minus -6, so 10.
Wouldn't it be -4 for the second?
No. Right, because it's 4 plus 6, you're minus an.
Because it's 2, 1, 5, right? For row 2, right? And then if you multiply row 1 by
2, and you subtract it.
That's -4, right?
Yeah, 1 minus -4 is 5.
Okay.
Yeah. Right, and then 0, -5 minus, what is that, 14? So -5 plus 14, that's 9. And then this is 27 and 18. Okay. So we got multiples, they're like obvious factors in some of the rows, and so it just makes sense to get rid of them. So we'll divide row 2 by 5 and row 3 by 9. So that becomes 0, 1, 3, 2, and the bottom row also becomes 0, 1, 3, 2. And then we'll kill the last row. Alright. So this is actually row echelon form, which is nice. Here are my pivots. Okay. And so we got 2 pivot columns, right? And then this last guy, we'll call that, we've been calling that a free column. And so now it becomes clear to us why we really call that a free column. It's because, right, remember each column corresponds to a variable, x1, x2, x3. So my last column then, corresponding to x3, tells me that x3 is a free variable. Okay? And why do we need a free variable? Well, it's because I have 2 equations and 3 unknowns, right? And it's not possible for me to solve that unless I make an assumption about one of the variables. And we'll just happen to make an assumption about x3 since it's a free variable. Okay? Alright, so that means I need to make an assumption on x3. I'll say x3. So you can just leave it as x3. That's like perfectly fine. I'm going to call it t. It doesn't matter. You can just leave it as x3, but I'm going to call it t. And then in row 2, all right, row 2, I have x2 plus 3x3 is equal to 2. All right, but I know what x3 is. What is x3? Yeah, it's t. So x2 is going to be 2 minus 3t. And then from row 1, I have x1 minus 2x2 minus 5x3 is equal to -3. All right. I I just solved for x2, which is 2 minus 3t, and I know x3, and x3 is t, and this is going to get me negative 3. Alright, and now I just need to solve for x1, negative 3 plus 2 times 2 minus 3t plus 5t, since we moved everything over, and then x1 is going to be, should we work that math out? It's like 1 minus 2. Okay, and so now here's my x vector. The solutions got 1 minus t. That's x1. x2 is 2 minus 3t. x3 is t. All right. And what is that? It's a line, yeah. Okay. And how many solutions do I have on a line? An infinite number of solutions. So, okay, so yeah, so I have 3 planes. They're intersecting exactly at a line. And again, if you're not convinced why this is a line, we can also write it in the 114 way, which is this. Negative 131 times t plus the point 120. Does that seem familiar? Yeah. So it's a line. We're just writing it all together as a column vector. And okay. And all right. So I have infinite number of solutions. What's the rank of my matrix A? Yeah, it's 2, right? So again, we're taking a look at rank A, and that's 2. And what's the rank of my augmented matrix? Yeah, it's also 2, because, well, there's no pivot here. So, go back. Now, I got infinite numbers of solutions. My rank is 2, of A is 2, and my rank of A augmented is also 2. So now I think we can start drawing conclusions, okay? And what are they? Well, if rank A is less than rank of A augmented, what happens? Yeah, there's no solution. All right? And then we see that these guys, if we do have a solution, or what's the term for us having at least one solution? Yeah, it's consistent. It's like, it's in the lump of terms I threw at you guys last week. But if the system is consistent, then rank A looks like it has to equal rank A augmented, okay? And then if rank A is less than A augmented, we say it's inconsistent. Okay, what else? Well, then what differentiates having one solution and having an infinite number of solutions? Right, okay.
The rank is less than the
columns, right? Okay, so now we want to compare our rank to the number of columns, right? Why not the number of rows? Yeah, so remember, rows were like the number of planes that I have, but we're trying to find like what our unknowns are supposed to be, and where did we like label our unknowns on our matrix? Yeah, we labeled them on the columns, right? Remember, x1, x2, x3 were the columns of the matrix, and so we want to compare the ranks to the columns. So if I just have A m by n in general, right? If rank A and rank A augmented are equal to n, then you'll have exactly one solution. All right, and in this case, since A was a 3 by 3 matrix, right? We took 3, and we see that since rank A is equal to rank A augmented, and they're both equal to 3, there's one solution. And then, if the ranks are less than the number of columns, we're going to have infinite numbers of solutions. Any questions? All right, so before we leave the session, review. Let's jump into one last example. I promised I'd graph on my test bank, and here it is. This is from midterm 1 from fall 2017. It's from I'm not going to name the professor. And here's you have the system 1, 2, 1, 3, 3, -1, -2, 1, 1, 3, 2, 4, 0, 2, 0. Okay? And it's just solve the system. So before we start, I guess, what kind of dimension, like what kind of space and what kind of shapes do I have?
R4.
Yeah, I'm in R4. And I have these like 4-dimensional weirdo thingies, right? And I have 3 of them. All right, so I got 3 whatevers in R4. Okay. So again, let's roll this. We already have a 1 here. That's great. So we just need to kill those guys. Row 2 plus row 1, and row 3 minus 2 times row 1 will do the trick. 1, 2, 1, 3, 3, 0, 0. So we're adding the rows. 2, 4, 6. And then this becomes 0, 0, -2, -4, -6. All right, and then I'm gonna do something that I like tell people not to do, but I'm essentially gonna kill the last row while simultaneously changing the row I used to kill the last row with. Sometimes you get like some computational errors, but in this case it's fine because we see that the last row gets killed, right? And then we see that we can just factor out a 2 from that middle row. So I'm just gonna do both simultaneously. Okay, and so now, here's a pivot, so we got P, P, and then here's F, and here's F, alright? So, of course, this is a midterm problem, right? They're not just going to have you have one free variable, they're going to give you multiple free variables, because otherwise it's not going to be hard enough. And so what we have to do then is, okay, so for each free variable that we have, right? Remember in the previous example, we assigned x3 equals t. Well, for every free variable, we just got to give it something random, okay? And so, what are my free variables in this case? Yeah, so x2 and x4. I'll start off with x4 because we kind of like to work backwards when we're solving systems of equations. So I'll let x4 equal t. And I'll let x2, we'll call it s. You can call it r. You can call it left parentheses. It doesn't matter. Okay. And then, so now, here's row 2, the equation from that row. I got x3 plus 2x2 is equal to 3. Alright, oh, whoa, x4. Okay, so then x3 is equal to 3 minus 2x4, but we know what x4 is, we call it t, so we'll call it 3 minus 2t. Alright, and then in row 1, I got x1 plus 2x2 plus x3 plus 3x4 is equal to 3. Okay, now that's x1 plus 2s, right? x2 is s, plus x3, which is this 3 minus 2t value we just put in, or we just found, plus 3x4, well, that's really 3t, that's equal to 3. Alright, and so now we just have to solve this mess. x1 is equal to 3 minus 2s minus the quantity 3 minus 2t minus 3t. Alright, I just moved everything over to the right-hand side. Yeah. So that's the last step is to simplify this. So, yeah, the 3's cancel out, and then you get like negative 2s, and then that's like a minus t. Alright, so here's our vector. x1 is negative 2s minus t. x2 is f, x3 is 3 minus 2t, and x4 is t. There we go. That's a solution. So we got three of these four-dimensional object thingies. They're intersecting at what? What is that? Yeah, it's a plane, right? Because if I had one parameter, it's a line, all right? Because it's one-dimensional. If I have two parameters, then it's two-dimensional, so it's a plane, okay? Or a surface. You can think of it that way as well. All right. So this is it's a plane / surface. It's whatever two-dimensional object you want to think of it as. All right. Okay. Any questions? One last thing I want to touch on. Okay. Let's jump to inverses. I'm not going to talk about the theory of inverses. Might do that a little bit next week. So this is 2.6, I think. We'll do a definition, and it's the definition of invertible. And you'll hear this word a lot, okay, coming up. Like the rest of the semester, like we're going to be saying invertible a lot. So we saw a matrix, n by n square matrix. Well, I guess that's what n by n is. An n by n matrix I is said to be invertible if there exists, all right, that's the backwards E, A inverse such that A times A inverse is equal to A inverse times A, which is equal to the identity matrix of n by n. And A inverse is also an n by n matrix as well. So we're only talking about square matrices here. And then we say that A inverse then would be the inverse matrix. So invertible, this is an adjective. All right, so we're doing some English in math class today. So think of an example of how to find the inverses. And this is from, not fall, it's from spring 2018. It's from last semester. All right, midterm 1. And it's really just find the inverse of this matrix B is equal to 1, 2, 3, 0, negative 1, 4, 0, 0, 1. You have to find B inverse. Okay, and so how do we do this? Well, we just create a gigantic augmented matrix. All right, we put B on the left-hand side. And we put the identity matrix on the right-hand side. Okay? So what do we need to do? So this is B, and this is identity matrix. So it's time. I'm going to run a little bit over here. So if you have to dial again, this is being recorded. So what we need to do then is, so step 1 is to get into row echelon form. All right, which the professor graciously has already given us almost row echelon form, but we need it exactly in row echelon form. So what we're going to have to do then is we're going to have to take the second row, right, and we're going to have to multiply by -1. Okay, because it has to be exactly row echelon form. It can't be anything like close to it. So so this was a -1, and so if I multiply through, then that becomes positive, that's a negative, and then this is a negative. Okay. Step 2 then is to reduce it into reduced row echelon form, which means I need to zero out these guys first. All right. So how do I do that? Well, what are my equations to zero out those entries? Yeah, so row 2 minus 4 row 3, and then, or no, it's not minus, it's plus, yeah, it's plus 4 row 3. And then I want row 1, anyone? Minus 3 row 3. So, okay, so row 3 stays that self. Alright, row 2, this becomes 0, 1, 0. Alright, this is 0, negative 1, and then I added 4 times row 3, so that's 4 right there. And this becomes 1, 2, 0, 1, 0, and then 0 minus 3 times row 3. That's a negative 3 right there. And then finally, the last thing I got to zero out is this guy, which is taken care of by row 1 minus 2 row 2. 1, 0, 0. Let's fill out the bottom rows first. 0, 1, 0, 0, negative 1, 4, 0, 0, 1, 0, 0, 1. Okay, this becomes 1, 0, 0. So I got 1 minus 0, that's 1. 0 minus negative 2, which is positive 2. And then negative 3 minus 8, that's negative 11. So you'll see what happened is that once we reduce this entire thing, right, this entire thing is in reduced row echelon form, right? Because everywhere with the leading 1 has zeros elsewhere, right? That's 0, that's 0, that's 0, that's 0. Okay? Since it's in reduced row echelon form, you'll notice that, hey, this left-hand side is the identity matrix, and this right-hand side is actually B inverse. Yeah? Here? Well, it's because the initial matrix was a negative 1 here, and I had to make that like a strict row echelon form, so I multiplied row 2 through by negative 1. Okay? And if you go back and watch the video, that's like the steps. I think I made that clear, but that's why it should have been identity matrix, but I didn't want to rewrite all 18 entries. Okay, cool. So that's it for this week. I have office hours later today, and homework's due on Tuesday, and I'll see you guys next week. I think we're going to be diving into determinants and maybe some vector spaces, hopefully. Yep. What? It's essentially you're essentially simultaneously solving all of the equations at once. So what you're actually doing is you're actually solving like 1, 2, 3, 0, negative 1, 4, 0, 0, 1 times x, y, z is equal to 1, 0, 0, right? And then you're also solving like x2, y2, z2 is equal to 0, 1, 0.
But what does that like conceptually mean? Why can you just solve for like
right? So that I'm just essentially stacking these columns together, which means I can stack these columns. Like I can just bind them like by columns.
That makes sense.
Yeah.
All right, thank you.
So,
I mean, that's specifically inverse. Sorry.
No, that's fine.
Sorry. So that's specifically inverse for the given matrix that for the problem. But then, like, if you were to put the matrix on the reverse echelon, it's like there's no point in doing that. It's like you want to find a matrix for the you want to find the inverse for the matrix at a given time.
so I'm not completely understanding where you're going at.
You use the row operations to get the matrix on the row. So if you use row echelon,
Yeah.
and you find the matrix. Then the matrix in this time.
Yeah, it's like
Right. Yeah, okay. Yeah. I think I explained it myself. It's just
Right. Again, it was the fact that we were solving, like, essentially we're solving 3 equations at once, and you can kind of just like stack, like each column is like a column of unknowns, right? And so we really, like, again, we wanted to solve like this matrix times that matrix is equal to, like, this matrix times some unknown was equal to 1, 0, 0.
Okay.
And then we also wanted like a second set of unknowns to equal 0, 1, 0. And then we also have a third set of unknowns where we wanted to equal like 0, 0, 1.
Okay.
All right. But then I can actually just stack them all together and solve it all at once by using the reduced row echelon form way of solving the augmented matrix.
Yeah.
Yeah.
All right, we'll move on.
Okay.
And so actually, I was actually in the other recitation.
Okay.
Accidentally, I was in E9.
Okay.
I didn't realize I was in E9 when I was doing the attendance.
Sure.
But yeah, I just realized that.
That's fine. I don't take attendance in my class. That's not how I'm taking attendance, like doing the extra credit.
Okay.
So yeah, don't have to worry about it. The way I'm doing extra credit is through Piazza.
Okay.
And so there's a link on my website if you're familiar with my website.
Nah, but
Okay.
I'll definitely check it out.
Okay, yeah. So if you check the syllabus on my website on there, it's also eigen-li.com. So it's just my first name dash my last name. It's pretty easy to remember. And yeah, I have all the recordings of the previous recitations as well. So if you want to check those out, and a bunch of videos.
All right, thank you. Thank you very much. Nice to meet you.
Yeah.
Thank you very much.
I'm a bit confused about what do you mean by where a leading one should be. Is that I should
So like, I could have a leading one here if I wanted to divide this row by -5.
already like row reduced form?
Right, exactly.
So if this is not zero, so I still need to turn it into.
Yeah, you still need to like row reduce it at least somewhat, right? Into like something that. So essentially, I said this is called exposing the pivots.
So I know that it could be one.
Right. It could be one, but you don't have to make it one because you can identify that that's going to be it.
Can you explain more about why this is a line?
Yeah. So there's a parameter, right? So if t equals 0, right?
Yeah.
I'm at 1, 2, 0.
1, 2, 0.
Okay. And if t equals 1, right? Then I'm extending, like, I'm at a different point away. And then if I keep on changing t, I keep on moving away from that point on either side. And so that's going to be like a straight line.
So this should be